Blind deghosting for automatic multi-exposure compositing. Let us look at the problem we address. As we all know, real-world scenes can take enormous range of brightness levels. That is, they have high dynamic range. However, common cameras, printers, displays can represent only limited dynamic range. Then, how shall we visualize real-world scenes using common devices which are compatible only with low dynamic range or LDR images? The common solution is to composite multi-exposure images to enhance the dynamic range. However, when camera response function or CRF is not known, one can generate LDR image directly by compositing multi-exposure images. Example of some of the methods are exposure fusion by Mertens et al. And bilateral compositing by Raman and Chaudhuri. Here is an example of a static high dynamic range scene captured via multiple differently exposed images. This figure shows the compositing result of an existing method. Here is another scene, but this one is non-static. Compositing using an existing method yields this result. We can see artifacts in the image caused by moving objects in the scene. These artifacts are popularly known as ghosts. Our objective is to remove these ghosting artifacts. We shall now look at the deghosting problem. So now the problem can be rephrased as how to visualize dynamic real-world scenes using common devices. In other words, how to avoid ghosts while compositing multi-exposure images without the knowledge of camera response function. High dynamic range imaging methodology which requires camera response function is as shown in this figure. Here are the references which explain the high dynamic range imaging methodology. For dynamic scenes, let us consider two techniques for avoiding ghosts in high dynamic range imaging. Here is the basic equation for image formation where the image intensity is related to image irradiance through the camera response function. When one has the knowledge of camera response function, the equation relating the log exposure of two differently exposed images becomes linear. This is as shown in the last equation. This fact is exploited by Gallo et al. Who performed motion detection in a patch by checking whether it follows the linear relation or not. This method enables one to create artifact-free high dynamic range image when the camera response function is known. This is achieved by assuming one reference image and detecting relative motion in other images. While compositing, patches which show appreciable motion are ignored. Other approaches described in Jacobs et al. Requires one to compute variance or entropy across multi-exposure images. As the motion regions are replaced by detail from only one of the multi-exposure images, these approaches lead to reduced dynamic range and contrast apart from providing poor motion detection accuracy. The approaches discussed till now lead to generation of artifact-free high dynamic range image. For visualization in common devices, one needs to tone map the high dynamic range image to an equivalent LDR image. The selection of an appropriate tone mapping operator is a challenge. However, in the absence of camera response function, it is possible to generate LDR image directly by compositing in the image domain. The basic methodology is shown here. Here are the references which generate an LDR image directly from multi-exposure images. However, these methods produce ghosts in the case of dynamic scenes. We propose a novel approach to detect motion in the absence of camera response function and generate an artifact-free LDR image. We assume one reference image and compute a sixth-order polynomial transfer function between each of the other images with the reference image. One such transfer function is as shown in the figure. Next step is to use a constant width region around the transfer function where static pixel locations of the test image should fall. Patches which have appreciable number of pixels which fall outside this region are identified to have motion. Apart from choosing a threshold for the constant width region, we also fix a threshold for the fraction of pixels lying outside the constant width region. The patches which have number of pixels lying outside the constant width region exceeding this threshold are classified as having motion. We then use exposure fusion by Mertens et al. To composite the patches without motion. This figure shows the proposed approach. The patches are chosen to have an overlap of 1 pixel and compositing on the patches without motion is performed. We compute the gradient of the composited patches and employ Poisson solver to generate an equivalent LDR image. This operation enabled us to remove any visible seams introduced because neighboring patches of LDR image might have contributions from different number of patches. Here are the results. Multi-exposure images of a dynamic scene are shown here. We choose the fifth image as the reference. Here we can see the patches marked as black which convey the presence of motion with respect to the reference image. These patches are ignored while compositing. After compositing, we see visible seams on some of the patch locations. After Poisson seam correction, which we described earlier, we get the final image as shown on the right, which has no visible seams apart from having no ghosts. Here is another dynamic scene captured using multi-exposure images. The third image is used as a reference here. We see the motion detection using our technique. Generated LDR image without any ghosts is shown here. Here are another set of multi-exposure images of a dynamic scene. This figure shows the LDR image generated without any ghosts. Here are the conclusions. We have proposed a novel algorithm for detecting motion in multi-exposure images, assuming no knowledge of camera response function and other camera settings. We show that we are able to generate artifact-free LDR image compatible with common displays and printers. As details are composited in motion regions also, the generated LDR image has high contrast. Thank you.